One Raptor engine failed mid-flight, and SpaceX watched it happen, live on camera. Flight 12 was supposed to be another milestone. Instead, onboard footage caught smoke pouring from a Vacuum Raptor seconds after stage separation. One engine down, the entire upper stage at risk. That single failure just forced SpaceX to tear apart everything on S-40 before Flight 13 ever leaves the ground. Now, S-40 has rolled out to the test site. A major upgrade is locked in, and SpaceX is pushing for a static fire that could decide whether Flight 13 launches in July or gets grounded again. What exactly did they change? Stay with me. SpaceX has launched Starship 11 times before Flight 12. 11 times of pushing limits, breaking records, learning from every single failure. And by the time Flight 12 rolled around, the mood inside Starbase was confident, almost too confident. Flight 12 was supposed to be the cleanest Starship mission yet. Booster 14 performed a flawless catch. The crowd erupted. It looked like SpaceX had finally cracked the code on full reusability. But then, the upper stage told a different story. Seconds after stage separation, onboard cameras picked up something nobody wanted to see. Smoke. Coming from one of the Vacuum Raptor engines. Not a small wisp. Not a sensor glitch. Actual smoke, curling out from the engine bay, visible in real time to millions of viewers watching the live stream. And then, the engine went quiet. One Vacuum Raptor, dead, mid-flight. Now, here is where most people watching the live stream moved on. The ship kept flying. The mission continued. SpaceX commentators stayed calm. So viewers assumed everything was fine. It was not fine. Because inside SpaceX's engineering teams, that single failure set off a chain reaction of questions that had no easy answers. How did it happen? Was it isolated? Could it happen again? But worse, on Flight 13? And most critically, could it happen during a mission carrying actual astronauts? That last question is the one that changed everything. What actually failed, and why it matters more than you think. To understand why this failure hit so hard, you need to understand what a Vacuum Raptor actually does. Think of Starship's engines like a relay race. The sea-level Raptors at the base of the ship do the heavy lifting during launch. They push against thick atmosphere, fighting gravity. But the Vacuum Raptors? They take over in the silence of space, where there is no air resistance, no friction, nothing slowing you down. Their entire job is precision, efficiency, delivering the ship to exactly the right orbit with exactly the right velocity. Lose one of those in the wrong moment, and you do not just lose power. You lose control authority. You lose trajectory precision. In a worst-case scenario, you lose the mission entirely. Now, SpaceX has not officially confirmed the exact cause of the Flight 12 Vacuum Raptor failure. That is important to note. What we know comes from two sources: the onboard footage showing smoke near the affected engine, and SpaceX's own behavior afterward. And their response told the whole story. Because within weeks of Flight 12, S-40, the next Starship upper stage, was pulled from its scheduled path and redirected toward a static fire campaign. That is not a routine decision. Static fire tests are expensive, time-consuming, and logistically complex. You do not order one unless you believe something is wrong, and you need to prove it is fixed before you fly again. So what are the likely causes? Engineering analysts following SpaceX closely have pointed to several possibilities. First, a propellant leak near the engine bay. The smoke pattern visible in the footage is consistent with a small but sustained fuel or oxidizer leak igniting in the low-pressure environment just outside the engine. Second, a turbopump issue. Raptor's turbopump spins at extraordinary speeds, fast enough that even microscopic imbalances can cascade into failures. Third, thermal stress. The transition between the lower atmosphere burn and vacuum ignition creates extreme temperature swings that can stress engine components in ways ground testing sometimes fails to replicate. Any one of these is fixable. But here is the twist. SpaceX does not need to know the exact cause to act. They need to know the failure cannot repeat. And the only way to prove that is to put S-40 through conditions that would expose any weakness before it ever reaches orbit. That is exactly what the static fire is designed to do. But there is a deeper question here that nobody is asking out loud. If this failure was truly isolated, why is SpaceX treating it with such urgency?
S-40, the vehicle that has to prove everything.
Let's talk about S-40 specifically, because this is not just any Starship upper stage. S-40 completed its cryogenic testing campaign back in early May, before Flight 12 even happened. That is a significant detail. It means SpaceX had already stress-tested S-40's structure with super-cold liquid nitrogen, checking for leaks, structural integrity, and pressure handling at the extreme temperatures propellants reach before ignition. S-40 passed. It was cleared. Engine installation was completed. And for weeks, it sat in Mega Bay 2 at Starbase, while engineers completed final checks and the world waited. Then Flight 12 happened, and the calculus changed. Suddenly, S-40 was not just another Starship waiting for its turn. It became the vehicle that had to answer for what Flight 12 left unresolved. Every Raptor installed on S-40 now carried the weight of that mid-flight failure. Every system had to be looked at through a new lens. Not just, does this work? But, could this fail the same way that engine failed on Flight 12? That is a completely different standard, and it requires a completely different kind of test. On the night of June 23rd to 24th, S-40 finally rolled out of Mega Bay 2. The move happened between 10 p.m. and 2 a.m., deliberately timed to minimize public visibility. Earlier that same day, a static fire stand arrived at Mega Bay 2, confirming the rollout was imminent. S-40 is now at Massey's test site, and this is where things get interesting. Massey's test site operates differently from the main launch pad. It does not require road closures. It does not trigger the same public notification requirements. SpaceX can move fast there, test on short notice, and keep results internal until they are ready to share. That operational flexibility is not an accident. SpaceX is telling you something by choosing Massey's. They want speed. They want control. And they want to keep the findings internal until they know exactly what they are dealing with. What they find there will determine everything about Flight 13.
What a static fire actually proves, and what it cannot.
Here is something most YouTube channels will not explain clearly. A static fire test is not just turn on the engines and see what happens. It is a precisely choreographed sequence designed to replicate the most stressful moments of an actual flight, without the vehicle ever leaving the ground. Engineers load the propellant tanks with liquid oxygen and liquid methane, chill the engines to operating temperature, run through ignition sequences, measure chamber pressures, check turbo pump behavior, monitor thermal readings across hundreds of sensors, and then cut the engines, all while the vehicle is bolted to the ground. The data they collect in those few seconds of firing tells them more about the health of those engines than months of visual inspection ever could. For S-40's test, SpaceX engineers will be paying particular attention to the Vacuum Raptors, the same engine type that failed on Flight 12. They will be looking for any sign of anomalous pressure behavior, any unusual thermal signatures, any turbopump vibration patterns that fall outside the expected range. If everything looks clean, S-40 moves forward, engine inspections, final vehicle checks, and then integration with Booster 20 for Flight 13. But here is the part that creates real uncertainty. Static fire tests simulate flight conditions. They do not perfectly replicate them. The transition from sea-level ignition to vacuum ignition, the exact aerodynamic and thermal environment at staging altitude, the specific sequence of events that led to that smoke on Flight 12, none of that can be fully reproduced on the ground. SpaceX knows this. That is precisely why the engineering teams will not just be looking at whether the engines fire cleanly. They will be looking for any red flag, no matter how small, that could hint at a deeper systemic issue. Because one thing is absolutely certain after Flight 12. SpaceX is not flying the next mission until they are confident they know what went wrong and why it will not happen again. The question is, how confident is confident enough?
Booster 20, the other half of the equation.
S-40 is only one piece of the Flight 13 puzzle, because Starship does not fly alone. Booster 20, the Super Heavy booster assigned to Flight 13, has its own testing timeline running in parallel, and it completed its cryogenic testing earlier in June, putting it slightly ahead of where most observers expected it to be. Now, B-20 is expected to undergo its own static fire campaign, likely in early July, following weeks of pad upgrades and validation work at the orbital launch site. Here is the significance of that timing. If S-40's test goes well in late June or very early July, and B-20's campaign follows shortly after, SpaceX could realistically have both vehicles cleared for flight within the same 2-week window. That would put a July launch firmly within reach. But, and this is a critical but, both vehicles need to pass. Not just one, both. If B-20's campaign reveals any problem, Flight 13 slides. If S-40's test uncovers something that requires additional engine work, Flight 13 slides. The margin for error here is essentially zero, because SpaceX has already communicated to NASA and to the public that consistency is the top priority for this phase of Starship development. And that pressure comes directly from NASA and the Artemis certification timeline. So the urgency behind these tests is not just about getting back in the air quickly, it is about getting back in the air correctly.
The upgrade nobody is talking about.
Now here is where the story takes a turn that most coverage has missed entirely. When SpaceX rolls a vehicle out for a static fire after an in-flight failure, they are not just testing the existing configuration. They are validating changes. Think about what SpaceX's engineering process actually looks like. Between Flight 12 and S-40's rollout, teams at Starbase spent weeks going through every system on the upper stage. They were not just inspecting for damage or wear, they were actively looking for design improvements. Small changes to components, material upgrades, modified assembly sequences that could prevent a recurrence of the Flight 12 engine problem. Some will only become visible when SpaceX discusses Flight 13 in post-mission briefings. But the changes are there, they always are. What kinds of upgrades are likely? Based on the nature of the Flight 12 failure and SpaceX's known development patterns, several categories stand out. Engine bay sealing and thermal management is the most obvious area. If the smoke visible in Flight 12 footage came from a propellant leak or thermal event near the engine, SpaceX engineers would immediately look at how the engine bay is sealed, how heat is managed around the Vacuum Raptor installation points, and whether any gaskets, seals, or insulation materials need to be upgraded. Turbopump monitoring is another likely area. SpaceX's Raptor engines already carry extensive sensor arrays, but the Flight 12 issue may have revealed gaps in what the existing sensor suite can detect in real time. Adding or upgrading sensors sounds minor, but it fundamentally changes how quickly engineers can identify a developing problem during flight. Software-defined engine management is a third possibility. SpaceX's flight computers can actively adjust engine operating parameters in real time. If the Flight 12 failure had any component that could have been caught earlier by the flight management system, a pressure problem, an unusual temperature reading, then updating the software thresholds and response protocols would be a direct upgrade with no hardware changes required. None of these are glamorous. None of them will generate a dramatic announcement from Elon Musk. But collectively, they represent exactly the kind of incremental, precise, data-driven improvements that have made Starship more dependable with every successive flight. And here is the part that makes this upgrade cycle genuinely significant. Starship is not like any other rocket program in history. Most rocket programs iterate slowly, a new version every few years, with years of development between major changes. SpaceX iterates between flights. The vehicle that flies on Flight 13 will be meaningfully different from the vehicle that flew on Flight 12, not dramatically different in appearance, but fundamentally more capable in the ways that the Flight 12 data showed mattered most. That is a competitive advantage that no other launch provider in the world currently has.
The bigger picture, why Flight 13 carries more weight than it seems.
Let's step back for a moment, because the story of S-40's static fire and B-20's testing campaign is not just a story about two vehicles and one failed engine. It is a story about what SpaceX is actually building toward. And that context changes how you think about every technical detail in this update. Starship is not just a rocket. It is the foundation of SpaceX's entire next decade. It is the vehicle that will carry Starlink satellites to orbit in numbers that dwarf what Falcon 9 can deliver. It is the vehicle NASA has contracted to land astronauts on the moon under the Artemis program. It is the vehicle Elon Musk believes will eventually carry humans to Mars. Every flight failure, even a partial one like the Flight 12 engine problem, creates ripple effects across all of those programs. NASA watches every issue and evaluates it against the certification requirements for the lunar landing mission. Commercial customers track Starship's development record before committing payloads. And internally, every failure that cannot be fully explained introduces uncertainty into SpaceX's own launch scheduling. This is why the response to the Flight 12 Raptor failure has been so methodical. SpaceX is not just trying to fix a broken engine, they are trying to demonstrate to NASA, to customers, and to themselves that Starship's development process is rigorous enough to catch and resolve failures before they become catastrophic. Flight 13 needs to be cleaner than Flight 12. Not because Flight 12 was a disaster, it was not, but because each successive flight needs to move the needle in the right direction. And after a mid-flight engine failure, the only way to move that needle is to prove, through testing, that the issue has been identified, understood, and resolved. S40's static fire is step 1 of that proof. B-20's static fire is step 2, and a successful Flight 13 with all engines performing nominally through the entire flight would be the final, definitive answer to the question Flight 12 left open. But what if Flight 13 reveals something new? What if the static fires pass cleanly, Flight 13 launches, and a different system shows unexpected behavior? That is the honest reality of building the most ambitious rocket ever flown. Every flight teaches SpaceX something that ground testing could not. Flight 13 is not the finish line. It is the next data point. And right now, everything, the S40 rollout, the static fire campaign, the B-20 testing schedule, is pointed at making sure that data point is a good one.
The July timeline. Realistic or wishful thinking?
So, can Flight 13 actually launch in July? Let's be honest about what that requires. S40 needs to complete its test at Massey's with no issues. If that happens in the last week of June or first few days of July, S40 then needs to return to the integration facility for final inspections and any post-fire work. That process typically takes at least 1 to 2 weeks. B-20 needs to complete its own campaign, likely in early July, and go through the same post-fire inspection process. Then both vehicles need to be integrated, S40 stacked on top of B-20, at the orbital launch site. Integration itself takes several days minimum. Then SpaceX needs FAA authorization for the launch. Starship has its own complex authorization pathway, and any significant issue discovered during testing could trigger an additional review. Add it all up, and a July launch is possible. But it requires nearly everything to go right on the first attempt. No unexpected findings during testing, no post-fire rework beyond routine maintenance, no FAA delays, no weather holds. Is that realistic? SpaceX has surprised the world before by moving faster than anyone thought possible. But they have also shown, particularly since the Artemis partnership deepened, a willingness to slow down and be thorough when the data demands it. The honest answer is, July is the target. Whether it becomes the reality depends entirely on what S40 and B-20 tells SpaceX over the next 3 to 4 weeks. The outcome is uncertain. The stakes are real, and the data coming out of Massey's test site will be the first real signal of which direction this is headed. That is where the data stands right now. S40 is on the pad. The static fire will answer what Flight 12 could not. If you found this analysis useful, like, share, and subscribe to the Space Brief. Drop your thoughts below. We read every comment. Hit the screen to keep watching.